Okay, so just a quick recap of what we did in the last class. We started off with the SR flip-flop, then we realized D flip-flop and then JK flip-flop. We saw how to create a characteristic table, a state table, and the characteristic equation. And we spent a lot of time on JK flip-flops working, especially eliminating the 1-1 condition of SR flip-flop and how that worked in toggling your output when your J and K are equal to 1, right? So the most important part as part of a JK flip-flop is when J and K are equal to 1, your next state output, which is what is the next state output? Q of t plus 1 is the next state output. Your present state input will be toggled, which means if your present state is 0, your next state will be 1. And if your present state is 1, your next state will be 0. So this was an important change with regarding to the flip-flops, JK flip-flops. So if you look at the JK flip-flop, so this is how your construction was, and obviously JK can be converted into T flip-flop. The advantage of the JK was realized using T flip-flop for whenever both the inputs are same. So we saw the characteristic equation and characteristic table for that also. We did a very simple example where I will be telling you about the proper method. This is this design, that is conversion of D flip-flop to T flip-flop can be done. This was based on a logic. Whereas there is a step-by-step procedure how to convert one flip-flop to the other flip-flop. And then we started discussing about the problems with the JK flip-flop. Why there will be a problems with the JK flip-flop was because you have two stages of inputs and outputs in case of a JK flip-flop. For that particular instance, for any flip-flop, in fact. So this is the first stage and this is the second stage. So where does this particular problem have is from the feedback network. So here from the output, you are giving the feedback. There is one feedback which is going to the first stage and there is another feedback which is going to the second stage also. And the same output is going. So when the same output is going to one stage and the second stage, it is very much evident that there will be an asynchronization problem, which means that there will not be any synchronization between its input and its output, right? So that is the problem we encounter here, and that condition is called as the race over condition. Okay, so that condition is called as the race over condition or race around condition, right? So we will discuss about this particular condition just right away now. Before that, in order for the designers to have a better control on your flip-flop, people decided that we must have some external inputs that will control the second stage separately and the first stage separately. Likewise, two external inputs were designed. One is called as the preset input and other is a clear input. Preset will set your Q value. Okay, preset. It will set your Q value to the desired value, which means that it will set your Q value equal to 1. Clear will clear your value. What value? Your Q value to 0. Right? And this has been employed very brilliantly here because this preset input, it is made sure that it will set this Q value to 1, and at the same time it will not allow this feedback 1 to change this gate's output. That is why this input has been given here, because the same feedback output is coming here, so that this output should not be altered. Similarly, the clear input is also that way. right? We cannot give clear input and preset input to the same gates, right? Then there will be a conflict. That is the reason we are giving this clear input to the complement output, so that complement Q bar's complement is Q, that will alter your Q value. And again, you see here that we are controlling this particular gate. At the same time, this particular feedback goes to gate number 1 here, and that should not alter this particular output. Hence, the same input has been given here also, so that you control both these stages. This was a very nice design. Now, if you look at the timing diagram, there is a small understanding that we must make here. We are going to take a peculiar case of JK equal to 1, 1, because this is where the toggling takes place. Now, with both the inputs, please see here that we are giving a 0 here and your clear value is 1. Now, let us assume that we are giving a preset value for three continuous clock cycles. Okay. Whenever your clear value is 1, what happens immediately? Your Q value will raise to 1, right? Your previous state is 0. Your next state will raise to 1 here, because your preset value is raised to 1, because we are setting your Q value equal to 1 here. So Q value will become 1 here. But the problem here is when your Q is 1, right? Obviously, we are controlling this. There is a feedback that goes from this particular gate to this particular gate, which will alter this output. And at the same time, since your clear value was 1, this will be 0. And so, yeah, this will alter again this particular gate number, say 3, and this will again go to 0. So this feedback again changes this particular value to 1, and this 1 will again change this particular gate value to 1. So what happens here is there is a toggling that is taking place between 1 and 0 till there is an external input from the clear. So once you give, since this is a logic 0 value, once you are clearing this particular value at the 8th clock cycle, your output goes to, your Q value goes to 0 permanently. So, but the problem that we encounter here is whenever your preset value is 1, right, there is a toggling that is taking place. What is the reason for this particular toggling? Because the reason for this particular toggling is this particular feedback, right? This feedback, whenever Q changes, it affects this gate number 4, and this output is also changed, and this in turn will change the output of gate number 3, and there will be a toggling that is taking place. Why this should toggle is, please make sure that J and K values are equal to 1. Okay, so that is the reason this is having the property of this toggling effect. So now how do you avoid this? And this particular condition is called as the race around condition. Okay, but ideally what should be the value? Whenever your preset value is equal to 1, your Q value, ideally it must be equal to 1 like this. It should be equal to 1 like this, but it is toggling between ones and zeros. Now let us see step by step what is actually happening. Though I explained it using the diagram, let us see in theoretical form. So what is a race around condition? We know that in the SR, in your SR flip-flop, whenever you had SR equal to 1, 1, because of that particular feedback line, we modified this SR flip-flop with a feedback line, which converted you to get the JK flip-flop. Now, when your JK flip-flop is 1, right? So listen carefully, when your JK flip-flop is 1, Q is 0. If your Q is 0 for a positive edge detection with a clock, what must be your next state Q value? Your next state Q value must be toggled value of Q equal to 0, which means that it must be Q bar. Am I right? So this will make your next state value equal to 1. That's what is written here. So after a time interval equal to the propagation delay, the two NAND gates in series, the output will change to 1 here, right? It is toggled from Q equal to 0. Now what happens? Now we have JK equal to 1 and Q equal to 1. Again, after some time, what will happen, because there is a feedback network, again, your output now will change to Q equal to 0. This will continue till your propagation time. It will oscillate between 0 and 1 till there is a certain value from the external input of clear, right? So this will continue to take place, and this particular condition is called as the race around condition, right? Whatever I have said it verbally in the using the diagram, it has been written here. Now, how do you avoid this? I mean, maybe a better diagram with other inputs instead of preset and clear. You can see here that whenever your J is 1 and K is 1, right, toggling will take place. When Q is 0, right, your next state will be 1. When Q is 1, your next state will be 0. So toggling will take place here. Similarly, the complemented toggling will keep on taking place, and you are very much uncertain towards the end of the JK input. You do not really know what is the exact output of Q and what is the exact output of the next stage value, which means that you are really uncertain whenever your J and K is equal to 1, right? When during your SR flip-flop, when J and K, when S and R values are 1, you do not know what will be this value. It can be either 1 continuously, or it can be 0 continuously, or it can toggle. But here it is keep on toggling. At any instant of time, whenever you cut short this particular J and K value, at times it may be 0, at times it may be 1. So again, you are left with the same condition as that of your SR flip-flop. You are undetermined what will be the values of Q here. So this condition is called as the race around condition. Because why it is a race around condition is because if you look at the horse races, right, there will be they will be running in different lanes throughout this particular loop, right? I mean, whatever you call it as, they keep on running around this circle, right? So that is, you are racing around a particular between the gates over indefinite number of times. So that is the reason we call this as a race around condition. And how do you avoid this, and what is the solution to it? What is the solution to it is because, can you immediately say what will be the solution? Though we have a control here, now the solution to this is we must stop the propagation of inputs from stage 1 to stage 2. Similarly, we must have a better control of propagation of gates from stage 1 output to stage 2 output. Okay, and how do you employ this? How do you employ this is especially using this gate value, right? How do you do that? And this particular solution is called as a master slave solution. What is a master slave flip-flop solution? That is, one flip-flop will act as a master and other flip-flop will act as a slave. Let me give you the configuration. So what is this master slave latches? You will have two stages, two set of flip-flops, in fact, the same configuration that we had, that is 2 NAND gates in the first level and 2 NAND gates in the second level. So the first 2 NAND gates will be considered as the master flip-flop, and the the third and fourth NAND gates will be considered as the slave flip-flop. Only difference here is that lies in this particular clock. A positive edge clock is fed to the master, and the complemented value of the clock is fed to the slave here. So this is the only difference. How does it improve our inefficiency? That is, whenever your clock value is 1, right? What does it mean? The first stage is active, and your second stage, now we are complementing the same clock and feeding to the next two, that is level 2 gates. So this particular slave is inactive. When your clock is 0, your master is inactive, but your slave is active. By this way, the flow of outputs from, that is from level 1 to level 1, or level 1 input to level 1 output, and level 1 output to level 2 output are controlled better using this complemented clock. Right? The same has been explained in theoretical fashion here also. That is, whenever clock is 0, output of your inverter will be 1. Am I right? Whenever your clock is 0, your output is going to be 1 here. So clock input of slave will be 1, which means that this particular flip-flop slave will be enabled. When slave is enabled, you will get your Q and Q bar output. Okay, so in this particular example, if you see, just a minute. In this example, if you see, this is a simple SR flip-flop. Master and slave, it need not be only for JK. It can be for SR flip-flop, even for T flip-flop or D flip-flop. Here an SR flip-flop has been taken. So if you consider that the output of a master is Y and Y bar here, the output of slave is Q and Q bar here. So whenever your clock input is 0, you are enabling your slave. If you are enabling your slave, your Q will get the output of Y and Q bar will get the output of Y bar. And which means that master flip-flop is disabled because your clock is 0. Now when your clock is 1, when your clock is 1, master is enabled and slave is disabled. So this master slave configuration can be constructed for any types of flip-flop. So here we have used an RS flip-flop. Similarly, you can have a JK flip-flops construction also. So the dotted lines that you see here, this constitutes the master flip-flop. Right? This is a complete flip-flop. The 4 gates has been taken here. Similarly, another kind of another flip-flop set is taken, and this will be a slave flip-flop. So the first 4 gates will be controlled by the master clock, and the next 4 gates will be controlled by the slave clock. Right? So by this way, we can control the movement of inputs from level 1 to level 2 and level 2 to the output. Okay. So any doubts here? Okay. So this master slave JK flip-flop is the solution to the race around condition. Any changes in Q will not directly affect, it will only get propagated to the master flip-flop. Whereas for your inputs to propagate from master to slave, you need to have this clock active for the slave flip-flops. So if there is any change in this particular value of Q, what will happen is your Q can come over here, but not here to the next stage. Why? Because this set of flip-flops is unaffected because of it is not at all active in fact. Right? So I hope you can understand this logic in a simpler manner. Okay. Now coming to the clock, how does the practical, okay, maybe additional, the same information. So whenever during the first, there seems to be a doubt. It was blinking. I thought there was a doubt. Oh my God, something else. Okay. All right. So whenever a clock, during the first clock, what happens is your master is enabled and your slave is disabled. During your second pulse, your master is disabled and your slave is enabled. And gates 1 to 4 will be your master flip-flop. Gate 5 to 8 will be your slave flip-flop. Again, let me show you the configuration. Please see here, this is one flip-flop. This is the second flip-flop configuration. All 4 gates has been taken so that, you know, we are very sure that the propagation of inputs and outputs are controlled in a better way. Now coming to the characteristics of a clock, as you see here, it will not be a perfect square pulse. It will not be a perfect square pulse, but there will be some kind of a trailing edges here. So the real signals, as you see here, do not look like this, but rather it looks like this, which means that this transition from 0 to 1, it will not be very straight with, I mean, please remember that this is time scale. This transition here is not going to be instant. Similarly, this transition is not going to be instant at one single time. This transition will take place, say for example, t equal to 1 nanoseconds to t equal to say 1.2 nanoseconds, right? So this transition will take some delay here. So this is how the practically your clock will look like. So which means that we must also make sure that our outputs are stabilized during the steady state values of our clock. What are the steady state values of our clock? This is a steady state value of a clock. This is a steady state value of a clock. We must make sure that our inputs or outputs are not falling under these transition stages, because when they are falling under these transition stages, then we cannot be sure of the correctness of our outputs. Okay. And there are definitions to understand this particular clock also. We define two times here. One is called as a setup time. These are definitions, and other is called as the hold time. What is this hold time and setup time is? Before your transition starts, the stable time that you witness is called as a setup time. Maybe we can go to the definition here. So there is a minimum time called a setup time, for which input must be maintained at a constant value prior to occurrence of the clock transition. Prior to occurrence of a clock transition. Similarly, there is a hold time. Before the applications of a positive pulse of your clock, the transition time is called as the hold time, which means that you should not operate anything during this hold time. Okay, so for which the input must not change after application of a positive transition of a clock. That is, if you are applying your input here, and if it is changing, that it means that it is a hold, you are a part of you are operating in the hold time. If you're applying here and if your input is not changing here, then it means that you are not in the hold time. That's what it means. Maybe we'll read it again. For which the input must not change after application of a positive transition of a clock. All right. Now we are into most important part of our course, which means that now we are going to play around with the flip-flops, right? It will be really an interesting design playing around with flip-flops. Again, there is a step-by-step methodology, which you will not find it in any books. Over the years, which I have developed, and here they are. So what is that we need to understand? Till whatever we have designed or we have studied about the different types of flip-flop, one thing that came to us were different tables, equations, right? So that is from where there only we started analyzing our flip-flops, right? So the first table that you must remember or you must have in hand regarding the flip-flop is the characteristic table. You know what is a characteristic table? Your characteristic table is a table where your next stage output will be in terms of the present stage output, right? So in I'll just write the part of the table here. If q of t plus 1, then it will contain as a function of q of t. Okay. Next that you studied was a characteristic equation. Now, what is a characteristic equation? It was a relationship that we got from the characteristic table, right? From characteristic table, we got a Boolean expression, which we called it as a characteristic equation. In addition to that, we also studied one more table, which is called as a state table, right? So ideally speaking, from state table only we got this characteristic equation, but we are not going to use this state table anymore. Now we are going to design, or we are going to find another new table called as an excitation table, because this excitation table helps us in lot of applications. If you want to design a counter, if you want to design a timer, you want to set up a time bomb, then you can design an excitation table. You can use these flip-flops, and with the help of an excitation table, you can design a timer. So what is this excitation table? The excitation table is a table that has your present state and next state as its input, and your S and R as its output. Meaning, if you want to have a certain outputs, then what should be the inputs? That's what it means. I reiterate again. Excitation is a table that has present state, which is q of t, and next state q of t plus 1 as the inputs, and S and R, or say for example J and K flip-flops, J and K as your output. What does this convey to us? That is, if you want a designated set of outputs, then what should be the inputs given? That's what this excitation table will give you. Say for example, I must earn ₹1,00,000 per month. Then what should I do today? That's what it means, right? So excitation table is also that only. We want a particular output. So what should be its input? So yes, let's start with an SR flip-flop. Let me read out a table that lists the required inputs for a given change of state is called as an excitation table. Now for an SR flip-flop, we know and how do we construct it? We construct it from the state table. In fact, I'll tell you how to construct an excitation table. So first let us write the characteristic equation for an SR flip-flop. Please remember that you must have all these characteristic equation in fingertips. You must remember all these equations from examination point of view. Okay. So when your next state q of t plus 1 is given as s plus q of t r bar, where your SR is not equal to 1, which is invalid for the last 1-1 combinations. So this is what is this particular table called as? This particular table is called as the characteristic table, and this equation is called as the characteristic equation. Now we studied another table which is called as a state table. Am I right? State table. In fact, this characteristic equation is got from state table, and for a state table is got from the characteristic table, right? So this is a loop. Now, how do we get this excitation table? We get this excitation table from characteristic table, or in other words, we can say that we get this characteristic table from state table. Okay, I'll tell you how to create this excitation table. We know that your excitation, don't look at the entries, huh? You will get confused. Don't look at this particular part. You will get confused. Okay, I'm going to teach you step by step. So in excitation table, q of t and q of t plus 1, which is the present state here, and the next state here as the inputs, and S and R are the output. Now straight away, now if these are the inputs, present state and next state are the input, what are the 4 input possible combinations? 0, 0, 0, 1, 1, 0 and 1, 1. These are the input combinations. Now we need to know what will be the SR values. In order to fill up these values, you have to have the state table here. If you remember the state table, we must go to the page number 187 of my notes. But for your convenience here, I have rewritten again. Right. So this is the state table. Okay. Now for present state and 0 and 0, you look at how the values of S and R are. Where is q and q of t plus 1, 0 and 0? Q is 0 here, q of t plus 1 is 0. Anywhere else, here there is 0, here also there is 0. Now look at the SR value. S value is 0 here, R value is 0 for 1 and 1 for 1. So what we do here is, whenever there is a change in the values of S and R, we just put a don't care value here. Okay, so S value is 0, which is not changing, and R value can be either 0 or 1. Then let us look at the next combination, 0 and 1. Let me erase the highlights here. Okay. Now, where do you have present state 0 and next state 1? You have present state 0 here and next state 1. Anywhere else, 0 here, X here. Then nowhere else, Q is 0. So when your S and your Q and Q of t plus 1 are 0 and 1, your S and R values 1 and 0, 1 and 0. So we just use that as it is. It is 1 and 0. When your present state is 1 and 0, where do you have that combination? You have 1 and 0 here. Anywhere else? Yeah, one more place, 1 and 0 here. And what is the Q of, I'm sorry, I should not look here. Okay, so I have to look Q and QT plus 1, right? So I have 1 here, I'm sorry, not this one, this particular one. I have 1 here and 0 here, anywhere else? Nowhere. So, and SR value corresponds to 0 and 1. And SR value corresponds to 0 and 1. And where do you have present state and next state 1 and 1? There must be multiple places. Let me erase. Okay, 1 and 1. So here I have 1, here I have 1, here I have not here. Here I have 1 and here I have 1. In these places, R value is 0 and S value is 0 and 1. So for S, we write don't care, and for R, we write 0, right? And this is the excitation table. This particular table is called as the excitation table. Now, what you should remember is, in case if you can remember the characteristic equation, that is fine. Otherwise, you have to remember the excitation table, right? This will come by practice. As you solve more and more examples, you will automatically remember what will be the values of these SR values for a given excitation values. Okay, so right now we will attempt to remember, but if you are unable to get, but over the by practice you will get. So when it is 0 0, it is 0 don't care. When it is 1 1, it is don't care 0. Otherwise, for SR flip flop, it is 0 1, it is 1 0, and for 1 0, it is 0 1. Okay, so this we will remember, and these two we will remember. We will attempt to remember, right? So, okay, we will revisit again and again, so that it stays in our brain. Okay, now let us look at the next flip flop, which is the JK flip flop. For JK flip flop, what is the characteristic equation? So your characteristic equation is this. This is what is your characteristic equation. And we have to, what is the characteristic table now? This is what is your characteristic table is. And from characteristic table, what we must do, we must write our excitation table. Again, how our excitation table will look like? We have our excitation table, present state and next state, and all possible 4 combinations of present state and next state are 0 0 0 1 1 0 1 1. We have to fill up these data. Now, again, if you want to fill up these data, you need the state table now. If you want the state table, we have to go back to page 190 of my notes. But again, I have written it here for your convenience. So let us see, where do you have 0 0? Present state must be 0, next state must be 0. The first 2 entries, present state and next state, they are 0 and 0. So your J value is 0, but K value is don't care. Similarly, when it is 0 1, you have 0 and 1 here. I have already written 1s, 2s, 3s, right, where you can find those mapping. So for 0 1, it is 1x, 1 0, it is x1, 1 1, it is x0. Again, we will remember. Please, always whenever you are attempting to remember something, always try to remember with some reference. Let us compare this with SR flip flop, so that if we can remember the same things together, then it will be easy for us, right? So for 0 0 and 1 1, it was 0x and x0. It was again 0x and x0 here, right? Both are same, right? And for 0 1, it is 1 0 here, but it is 1x. 1 0, it is x1, whereas there it is 0 1. I think we are slowly catching up how to remember the excitation table values. Okay, we will again When we revisit again, we will do this. So we follow the same process. Now we have two flip-flops. One is an SR flip-flop and other is a JK flip-flop. Out of these two flip-flops, you can use any of these flip-flops to implement an application. Let us assume that I'm designing a counter, or if I'm designing a timer, or I'm designing a counter. Okay, I'm designing a counter where I want to count from say 1 to 100, either in the forward direction or in the reverse direction. I can implement. Okay, now I have to decide what kind of flip-flop am I going to use. I can use SR flip-flop and I can use JK flip-flop also. Don't worry about the 1-1 condition here, because 1-1 condition you are not at all getting in the excitation table. Am I right? S and R, they are not 1 and 1 at the same time. You see here, only 0 and don't care and zeros. If one is 1, other is 0, one is 0 and other is 1. So we are not at all getting 1 and 1. So we need not bother about this state at all. Which means that if I want to implement a counter, I can use either SR flip-flop or I can use JK flip-flop also. But out of these two, what is which is advantageous, which will give me less amount of gates? The answer to this particular question is your JK flip-flop will give you a simpler circuit and lesser number of gates. Obviously, then if there is a lesser number of gates, the cost of implementation will also be less. Why JK flip-flop will give me a simple circuit and SR flip-flop will not give me a simple circuit is because of these two conditions. These two conditions are fixed, right? Whereas here, instead of those two conditions, I'm having a don't care cases here. Because of this don't care cases, my circuit is bound to get simpler, right? So obviously we will always use our don't cares to our advantage, right? So again, here also it applies. Because of these don't care conditions, we will get a simpler circuit, or either we will get a simpler circuit or we will get a circuit something similar to SR flip-flop, which means that JK flip-flop is always a better flip-flop when compared to the SR flip-flop, which gives us a simpler circuit and a reduced cost circuit also. So this is what has been written here. So JK flip-flop illustrates an advantage of using this type of sequential circuits, and why is that there are so many don't care conditions in the JK flip-flops, right? So that the input functions are likely to be simpler. Either it will be same as SR or it will be simpler than SR. Okay. Now similarly, following the same process, you can create the excitation table for D flip-flop also. So what will be, I mean, D flip-flop and T flip-flops are not really exciting, but once you implement a JK flip-flop, it will not be too difficult for you to implement T flip-flop or a D flip-flop, right? So what is the process? First, we write the characteristic equation of a D flip-flop. We create the characteristic table, and from characteristic table, we get the excitation table. We all know that your next state is not dependent on your present state in case of D flip-flop. Hence, your present state and next state, they have no correlation. It all depends on if your next state is 0, 1, 0, 1, your D flip-flop input will also be 0, 1, 0, 1. So no need to go back and refer to the state table of this. If you want, you can definitely go back to page 188 and refer the state table. Similarly for a T flip-flop also. T flip-flop, it is dependent, but they are complement of each other. Meaning for Q and Q of T plus 1, if it is 0 and 0, then if 0 is changing to 1, it means that the toggling is taking place. So your T will be 1. If 1 to 0 there is a toggling, then your T is 1. Else your T is going to be 0. When there is no change, your T will be 0. Again, if you want to go back and look at the state table, go to page 191, draw the state table, and then you can create this excitation table, right? Okay, but still we understand from the logic itself, right? Any doubt till this? We have set our basics strong now. Now, shall we recall our remembrance? What will be the excitation table value for a JK flip-flop when their present state and next state are 1 and 0? Anybody? I'm just trying to recall how many of you have attempted to remember. Because we should not by heart, right? We have crossed the staging of by hearting after class 10 or 12. We should never by heart, right? We are all going into professional courses and we are now almost 50% professional, right? So we should not by heart anything. We must understand the logic and then we must answer. So anybody, what is the excitation table JK output, JK inputs for a present state, that is Q of t and Q of t plus 1? Just a simple quiz. When their inputs are 1 and 0, can you give me the J and K values? Okay, forget about it. So again, we are revisiting again so that we can do 1 and 0 is x and 1. Okay, and 0 and 1 is 1 and x. So we will revisit again and again so that till the time it goes into our brain automatically without by hearting. Okay. So next, what we have almost time to conclude our class, but I will touch upon something and then we will stop here. Now, why did we do all these things? Why did we do all these things is because we did an example of converting one flip-flop to the other flip-flop, that is T flip-flop to the D flip-flops, where we have traveled so far. Yeah, this example. If you look at this particular example, we want to convert T flip-flop from D flip-flop, which means that this D flip-flop is the source flip-flop you can consider, and this T flip-flop is the wanted flip-flop, right? This is the wanted flip-flop. Now, what is the logic behind this? If it is something like you are having some source and you have to use the particular source to implement something else. So which means that what is that you are having? You are having a D flip-flop. So the flip-flop that I'm having, so this will be my source flip-flop. What if I want to convert this source flip-flop into the wanted flip-flop? What I will do is I will create some external circuitry here. In this particular case, you see I'm having an XOR gate. I will use an external circuitry. And what is this external circuitry? This is nothing but a combinational circuit, right? Here we are having just a single gate. At times you might have combination of gates also here, an AND gate, OR gate, NOR gate, XOR gate, any combination you can have it here. So I will be having a combinational network here. So, and obviously the inputs will be there, inputs of this combinational network, and the output of this combinational network is fed back to my flip-flop. So I will feed this back to my flip-flop. Now, if you look as an overall picture, if I look at the overall picture, a combination of a combinational circuit and my source flip-flop that is available, this will represent a particular application. So for example, T flip-flop. This combination will look like a T, will give me a T flip-flop's experience, but which is implemented using a source flip-flop or a D flip-flop here. So the logic behind in understanding this is, if you want to convert from one flip-flop to the other, then this is how their conversion logic will look like. Let us say we want to convert flip-flop type A to type B. So the general block diagram is given like this. So type A is the given flip-flop. Type A is the given flip-flop or the source flip-flop. And if you want to convert this into another flip-flop, you will have a conversion logic or a combinational circuit. Okay. And these are the outputs of the required outputs of a desired flip-flop. And these will be the required inputs of the desired flip-flop. Okay. Now, if you look as a complete block diagram like this. If I want to convert, if I want to convert an SR flip-flop to a JK flip-flop, which means that the given flip-flop is an SR flip-flop. So its inputs are going to be S and R. Its output is going to be Q and Q bar. Okay. Now, there will be a conversion logic to do that. My inputs to this conversion logic will be the inputs of my desired flip-flop here. J and K are my inputs. So J will be my input and K will be my input to the conversion logic. And my outputs will be the outputs of my J flip-flop and my JK flip-flop. Okay, so this is what we are going to see, the conversion of one flip-flop to the other flip-flop. I'll just go through. There are a lot of steps. Then we will do it in the next class. Yes, there are a lot of steps here. So I have touched upon the logic, how we are going to convert. We will take one example in the next class and then we will complete. Yeah. So any doubts? Okay. If there are no doubts, then